matching and merging. Okay, I consent to recording, which have been sort of driven by trying to push what we have in terms of matching and merging beyond the currently possible. Now, let's get started with sort of just telling you about the outline and the goals. So today, I will sort of cover fixed order basics and NLO matching. Also, a few gory details of NLO matching. I hope I have kept things at the level that it won't get too technical, but still sort of point you at one or the other pitfall which could happen there. And then tomorrow we'll be looking in quite some detail into NLO multi-chat merging, which allows us to facilitate combinations with next to leading order. That not meaning matching, but I'll tell you about that difference. And as I said, some outlook maybe on shower development time permitting. I will also, something which I've been thinking about a lot, because there's a lot of development now going on to extend matching and merging towards other interactions, but I will limit myself to what we sort of do off the shelf and what we have available in event generators off the shelf, which is QCD corrections. And the QCD corrections which we have in mind in sort of expanding in just alpha S at a sufficiently large scale as a small expansion parameter, which we have available and which we do want to include in event generators, are clearly the first order correction, which is next to leading order correction, but we're now doing sort of routinely in the established event generators, and then at the next order we will be looking at next to leading order cross section. So this is just to set some notation. This is just a hard process, so this you should keep in mind when I'm talking about leading order, next to leading order, and so on. This really means fixed order perturbation theory for the hard process, and we'll be seeing soon how this fits into the all order picture of the pattern shower, which I think Stefan Prestel has already outlined to me. Now, nevertheless, when talking about matching and merging, I do feel that it is really necessary that we talk in detail about the structure of fixed order perturbative corrections to a given process. And this is sort of to understand how we can remove the double counting which we will identify between those and the pattern shower, and how we can assess systematics resulting from this picture. So what I've written down in the formula here is an NLO cross section for a certain process. So in the so this is not the differential cross section. I'm sorry. What I wanted to write is the NLO cross section as a function of a certain observable, and the observable typically has a yellow color. So this is just a function which defines what I want to measure. Now, in a Monte Carlo context, as you might have seen, this guy will sort of never make its appearance as an explicit function, but we will just calculate its value from a phase space point and fill in a weight. But it's important in trying to understand the structure that we keep this just as a function, and we look at the cross section as kind of a function of that observable. Now, in order to calculate next to leading order QCD corrections to such a process, I've picked here, to be precise, a Z plus 1 jet production in hadron collisions, where the C is the Turkey sky. I have a leading order matrix element, which I calculate from just tree-level graphs squared, and then I have virtual corrections, which by themselves involve an order alpha S relative to the leading order process, and then I have real emission corrections, which sort of involve a square root of just a single strong coupling for that single vertex emitting the additional gluon or describing additional gluon splittings. So it's clear that these two contributions will enter at different phase space dependencies, and that I've written down. The virtual corrections interfered with the leading order matrix element. That is the object which is of order alpha S on the one hand, that will fill the same observable on the Born phase space point as the leading order matrix element will. So this will just alter, in a sense, the weight of the Born contribution. And then for the real emission matrix element, if we square this guy, we get another order alpha S contribution, which we need to account for at next to leading order, and that will fill a real emission phase. Now, this cross-section, the ingredients to that cross-section, as you might have seen, they are horribly divergent, so they are not physical contributions to the cross-section individually, and so we need to make sense of that somehow. We'll be having explicit divergences in doing the loop integral, saying dimensional regularization will get poles in 1 over epsilon, and then we will have divergences being implicit in that real emission matrix element as the gluon becomes emitted at low energy or collinear to one of the jets or the incoming beams. Now, if we have a suitable set of observables, I'll tell you in a minute what I mean by suitable, then we will see these infrared divergences canceling out of the game, and the remaining divergences in the virtual contributions are of ultraviolet origin, and they will cancel by means of renormalization. So how does this look in detail, and why do we actually want to include fixed order calculations? And this is also something which I think is a prerequisite to thinking about why we want to do merging and so on. Now, clearly we want to do merging because we want to improve on the theoretical accuracy of the hard cross-section we start from. Now, this correction to the hard cross-section is not only given by virtual loop graphs, but also by real emission graphs, and we'll see that these will give rise to an additional jet. But as long as we're not explicitly asking for that jet, we'll get a correction to our leading order process. And the advantage is that sort of we can really observe that we stabilize this in the perturbative series as the dependence on the arbitrary renormalization scale will be then postponed to an order higher. And this happens by virtue of observing the running of alpha S, which comes out of the renormalization of the strong coupling. And then we will also see that virtual graphs will, together with the leading order, exhibit an ultraviolet divergence, which will give us a logarithm of the renormalization scale, just opposite to what we obtain from renormalization at this order in alpha S. And so we will have postponed the renormalization group dependence, the renormalization scale dependence of the cross-section, to one order higher, and get a more stable result, which we can also then estimate corrections by varying the renormalizations. The additional jet is more important, and that is the thing which actually is really relevant for merging. Not only that we want to improve on normalizations, but we want to improve on observing additional jets. But also here, next to leading order calculations should be taken with a bit of care, and I've depicted this here in that simple toy process of C+1 jet. If we look at this at leading order, and we look at the PT spectrum of the Z boson, say in this process, we will have that this single parton recoils exactly against the emitted Z, and so if we place a PT cut on the jet, we'll see that spectrum starting at the PT cut, and then it will drop. Now, if you calculate next to leading order corrections to it, we'll get a change in that contribution due to the virtual corrections, but we will also be able to emit an additional jet, and that will allow the Z boson to acquire a smaller transverse momentum than the transverse momentum of the jet we require, and we will see that spectrum here filling up below PT cut. And despite the fact that we have been observing this as part of a next to leading order calculation, which will give us next to leading order accuracy in the process we were really asking for, below here, we will only get leading order accuracy. And this is because of the fact that we will look at the real emission, and the real emission by itself is a tree-level process and is leading order. So this you should always keep in mind when looking at matched corrections. Ask yourself, am I asking the next to leading order correction for an additional jet, and then I will only get leading order accuracy, or am I really looking at the region where I am now next to leading order accurate? And that problem, resolving that problem, trying to make this region here also next to leading order accurate, that will only be possible if we look at multi-jet merging. So let's go back to how we make sense of these infinities. Now, if we look at the virtual corrections after renormalization, then the remaining epsilon poles, they will only be of soft or collinear origin. And the real contributions will deliver equally and opposite sign divergences to the virtual ones, and that sort of suggests that we could handle this by subtracting out one divergence from one of the contributions and adding it back to the other one. And that is exactly what is usually referred to as the subtraction formalism. And this I have been pointing out here. So the NLO calculation we had seen before, the NLO correction is sitting here. We have the virtual contributions, we have the real contributions. The virtual will depend on the observable evaluated at phi n, at the phase space point of n partons, and the real one will be evaluated for n+1 partons. Now, if I was to calculate a specific observable, say the PT of the set, and I could calculate this analytically, I would be able to observe that all of the infrared divergences cancel. But clearly, for more complex processes, we do want to do this by means of a Monte Carlo, and that is also the required input to build an event generator on. And so the subtraction formalism is essentially set up to come up with an approximate cross-section which is able to cancel the divergences in the real emission. And if it will cancel the infrared divergences in the real emission, then for sure, if I add it back to the virtuals and I am able to factor my n+1 parton phase space into a single parton phase space and an n parton phase space, then I should observe that the epsilon poles in between this and the analytic integral of this, they will also cancel. And the emission, I have written this auxiliary cross-section, I have written in a bit of a weird form, where these indices, which I'm contracting with some kernel V, should indicate that there are spin and color correlations if we have an additional emission, which we need to take care of to really locally in phase space cancel the divergences, which are obtained from the real emission matrix element. And then I have a kinematic map, because I truly want to add and subtract 0. So I need to evaluate this observable at phi n, and here I just choose to map back phi n, express that as a function of my n+1 parton phase space, and then I can factor it into the single parton phase space with some Jacobian factor, which we'll come back to later. And I have not changed anything, and now I have two individually finite contributions. Now, if we would want to generate events from these calculations, then we would have a problem. And the problem is immediately present in this contribution here. And I'll come back to this in a minute. So if we had only the same phase space point and a finite weight, then we could generate events like from a leading order Monte Carlo. But what this calculation is telling us, that we have something divergent for phi n+1 and something divergent which would generate events with only n partons. So this is some kind of a composite event which we will take, which we need to take into account in the fixed order calculation, but we can't use that to combine with a parton shell. And there's a further restriction to this construction, is that we can't do this with arbitrary observables. Now, first of all, we're doing a parton level calculation here. So we would calculate something like a jet cross section, in which we later on would include hadronization by some means of a hadronization model. But even then, I could ask questions about observables which would not be so-called infrared safe. And only infrared safe observables are really able to be calculated within the realm of these fixed order calculations if we do it in the simple way we have done it here. And that means that the jet observable dependent on phi n+1, so on the n+1 hard partons +1 emission phase space, is approaching its underlying Born value whenever I emit a soft gluon, or my gluon becomes collinear to one of the quarks. Now, there's no collinear divergence for massive quarks, but oh, this is a fun auto completion thing. Okay, this should read parton. There's no collinear divergence for massive partons, but there might still be enhancement which one would want to deal in this way. Then also the mapping I've been employing needs to satisfy the criterion that it approaches the underlying point, and then we can clearly see that in this case the divergences in between these two contributions here cancel. Generally, the difference will only be integrable singular, but that is a is a technical complication which we don't need to worry about here. So we've set up this this calculation for the fixed order. As we said, we could ask, could we generate events from that, just like for leading order one, and this will not be possible, and especially it will not be possible because we have this different phase space of different multiplicity with 100% correlated contributions as they cancel large numbers from one into the other bin. So you could think of this in a practical purpose, that we would look at some of observable u of phi, and then we have two bins, say, and what we do expect is that whenever we get singular with the real emission and we get singular with the subtraction term, we would observe that the real emission would provide a large positive weight in one bin, and the configuration for the subtraction term would not be far off, and we would get a negative weight in here, which in sum then gives us a finite weight. Now, in a little example, which I just put here in a toy model to illustrate a bit how this works in dimensional regularization, I'm just imagining a one-dimensional real phase space, and my leading order matrix element for C plus jet production, I have simply been simplifying to just a bare coupling alpha naught. And then the virtual corrections I can write in a form that I get an epsilon pole of UV origin and an epsilon pole of the infrared origin. And the important thing is that these poles factor towards the leading order amplitude and leading order here. And that allows me to combine them with an equally universal infrared behavior from the real emission. And in this case, my real emission would be something which diverges, which is this kappa over x to the 1 minus epsilon. So if I send epsilon to 0, I get a logarithmic divergence here. And then I have some finite contribution to it. And so I could construct a subtraction term which would just read like the divergence I see here. And if I integrate this analytically, it would go away with the infrared pole here. And the other pole would be taken care of by expressing the pair in terms of the renormalized coupling. So in the end, we get a finite cross section, and that is in this toy model depicted here, and we'll be especially focusing on the difference between the real and the subtraction term. This is really what where the double coupling with the parton shower occurs, and we can leave the finite virtual contribution aside if we have fixed our conventions on subtraction terms. And then the real one will be just whatever coupling I choose as a small parameter to expand in, and then we will have some kind of finite observable u of x sitting here, which is coming from this term. And then we will have the divergence, and the divergence will typically appear in that combination, that we will have divergence times observable on the real emission phase space minus observable on the phase space without the real emission. So this is in a toy model how a next to leading order calculation in subtraction would work. You can work out what the virtual contribution in this case would be. I think I've just adjusted it so it would just disappear. And then we can look at what we would get in terms of a differential distribution. Here you can already see that this is not well defined. We have something which is sort of a plus distribution type thing in here. So this means we get leading order contribution and virtual contributions and subtraction term contributions proportional to a delta function at x equals 0. And then the real emission, which would still have that divergence. And the only thing we can then observe is that if we would integrate over x in a range which contains the virtual and the real emission divergence, then we would get a finite weight, and then we can also think about generating events in that bin. Now, this is about the art of matching to next to leading order to parton showers, that we want to use a parton shower to essentially smear this bin content over a physical shape of the PT spectrum, such that in the end we will recover the fixed order cross section. And that is what I'll tell you about in the remainder of this lecture. What we should also understand about is clearly the structure of the parton shower, and I just want to use this as a tool to illustrate different contributions from shower type and also multi-jet type setups to the same observable, and effectively we'll start with a very simple observation on expanding this logarithmically enhanced series for an infrared sensitive observable up to the next two leading order, and then later on we will go on. So the infrared sensitive observables is essentially the class of observables which we model in with the event generators, with parton showers in particular. They receive contributions from all high multiplicity partonic final states, and we want to convolute them with some phenomenological model in the end. They are infrared safe, and to be more precise, they are recursively infrared safe. So they need to satisfy infrared safety for many emissions in an iterated way. And all of them are sort of infrared sensitive, and they measure the deviation from an n-jet topology towards an n+1 jet topology, either in an exclusive way, and that we will only make a transition from n to exactly n+1 jets, or in an inclusive way that we can only tell apart an n-jet topology at a certain resolution from a larger than n-jet topology. And classical examples is simply like thrust in E plus E minus going to Q bar, which is the blue example over here. The PT of the C boson, if this was an incoming quark and anti-quark, and we have an outgoing E plus E minus, or the delta phi between two jets in dijet events. And all of them have in common sort of that they have a value which is referring exactly to the Born contribution, and then they have a continuous spectrum at any value which is different from this, and that continuous spectrum, or if we combine that contribution from this exact n-jet limit with the continuum spectrum and integrate in terms of a cumulative spectrum, then we will get a dependence on our resolution parameter tau, which told apart n from n+1 jets, which involves powers of logarithms per power of alpha s. And this is why we actually need to resum these contributions to all orders, and that we do in an event generator using a parton shower algorithm, which is just modeling how multiple emissions come into this. So let me illustrate this for a few fixed orders, and then we will actually be able to use that graphic as a tool to see how we perform matching and merging and which contributions we get right with this. So what I'm trying is to visualize this series over here. And I'm trying to visualize it in the following way, that I want to distinguish the jet multiplicity I'm interested in by some kind of measure which resolves a certain number of jets. So what I'm putting on this axis is my kind of exclusivity and resolution, or a jet bin if you want. So, and on the other hand, I would just count orders of alpha s, and as this series here suggests, is that per power of alpha s we get up to 2 power of logarithm, and that we somehow need to deal with. Now, I could also integrate over that resolution parameter and ask myself about an inclusive cross-section. And then we'll see interesting things happening. But let's start with just the example again of C plus jet. So imagine that is a lepton pair balancing in PT at the leading order, as I only have a Q and a Q bar incoming. That is my leading order cross-section. I have no additional power of alpha s. I have no additional jet. I have no logarithm, and I just get, if you would want to look at it, the rapidity spectrum of this E plus E minus pair determined by the PDFs and the lowest order cross section. Now, if we start to add radiation to it, we could add virtual corrections and real emission corrections, which are below our resolution, and so we would still classify an event like this as being of zero jet nature because the additional radiation was not resolved. And then we would observe the first power of 2 logarithms and possibly some finite contribution. And that would sort of give us the next to leading order answer for topologies which exclusively have no additional jet. And as you can see, if now this resolution parameter becomes small, these logarithms will become large, and even for a small alpha S, that would not be a reliable answer. But let's push on and add some more orders. So at the resolving the first additional chat, so I'm opening up an additional chat bin here, I would get again alpha S and up to 2 powers of logarithm. And then if I would integrate over this, something interesting happens, that really these logarithmic enhancement in this case goes away, and I get a finite next to leading order contribution to the cross section. That will become an important concept later on, and that will also link to the pattern shower. And then I can move on, so I can sort of add additional unresolved radiation to my 0 chat bin, and I'm probing the first power of alpha S squared. I can go on and I can do the same with the first additional chat. Now I would get the first chat spectrum at next to leading order, and I would move on and eventually add in tree level 2 chat production, and then I would get the inclusive next to leading order correction to the process of C production. So now you get that pattern. Then if we ask that next to leading order correction for 2 additional chats, we will only get a leading order answer. And if we ask it for 1 additional chat, we will only get a next to leading order answer, which is this correction here. That is the next to leading order correction to the first additional chat. So 2 chats out of this next to leading order are not next to leading order, they're just leading order. That is important to keep in mind. Now, pattern showers, as you might have heard on the contrary, are derived in the soft and collinear limit, where we use sort of universal splitting kernels which factor off the cross section, and then we will actually be able to dress up such a leading order event with multiple radiations, and possibly we can be doing that up to a next to leading logarithmic level. That very much depends on the observable, which is something we'll come back to soon. And the pattern shower will then render these logarithms, which would sort of give us an unreliable fixed order prediction. It would sum these up to all orders and give us a physical result, and we'll depict this in a minute. So what we use is an iterative process where we factor the n+1 pattern cross-section in terms of some ordering and some splitting kernel, and then we can generate all of these logarithms by emission and no emission probabilities. And it's so important to distinguish angular ordered from dipole type pattern showers, as they deliver very different features, and they can predict different properties of observables, or different observables at all. Comparing this to fixed order, what will happen is that we will be getting say a leading order answer for the PT. Sorry, is there a question?
Not really stressed. On my back.
So if we ask for the PT of the C and in the next to leading order calculation, for example, then we will only get a leading order answer at the next to lead, which will diverge for PTC going to 0. At the next to leading order answer, we will get in the tail, we will get something more reliable, but also this next to leading order, which is the next to leading order for 1 chat, will diverge to at small CPT. So none of these fixed orders is actually usable. And the only physical answer we get, if we sum up all of these orders using our pattern shower, and we'll get a physical behavior for the peak, we'll get a finite value at 0 PT. Not 0, by the way, but a finite value. The region we can't tell anything about is the large PT Z range, where we really now need to supplement the initial process by the C+2 chat process and higher orders to get a reliable answer. And this is what matching is about. Now, in a bit more quantitative terms, we can look at the pattern shower as this iterative procedure, that it will just give us a no emission probability, and then it will give us back the observable we started with, if we think about this acting on an observable function here. And then we will get contribution starting from this hard scale Q. We will evolve down to a smaller scale at which we would then generate an emission, and then we will move on with the pattern shower from a new phase space point. And crucially, a new phase space point we obtain by by a mapping, by a kinematic map from the n parton phase into the n+1 parton phase space. It's very similar to the map we have seen in setting up the subtraction terms. And this is actually the gory details one needs to keep track of in setting up a consistent and comprehensive matching calculation with a parton shower. Now, on top of this, we have the unitarity of the parton shower. So this means if we really look at an inclusive measurement, the parton shower will give us back a unity and will be unitary, and that is at the heart of canceling these logarithms, which we would not expect to be there in the inclusive cross-section. And this is actually a constraint which we will be later on employing in setting up the most flexible and most sophisticated merging algorithm, which we can use towards next to leading order and even kind. It's also important to understand the accuracy of parton showers. This is something probably Stefan has been telling you about in more detail. I just want to do a very sketchy reminder of this. So if I'm looking at an observable which is really probing globally the deviation from a certain ideal two-jet topology like this here, then I can use the property of QCD coherence, and we can actually predict these observables at next to leading logarithmic accuracy. And for non-global observables where I only probe jetty properties in a limited patch of phase space, actually the whole complexity of QCD amplitude strikes back, and I need to have a dipole shower algorithm, which I can only construct in the large NC limit, but this will give the right answer then here. So this is one of the reasons which brings us to use dipole shower algorithms, and it's simply a question to what extent we can reproduce these coherent branching algorithms from dipole shower algorithms, because they also have the advantage that we can formulate this kinematic map emission by emission. So they are extremely well suited for next to leading order matching. So let me skip this. So the important point is, and I think Stefan has been reminding you of that we can construct dipole showers which do reproduce all of these classes of observables. And that is an important starting point for next to leading order matching as well, because we can expand these parton showers to fixed order, and we can employ the fact that they will be able to reproduce the structure of divergences which we encounter in the next to leading order calculation. That is a pretty crucial point in order to set up parton shower matching. Let me do one thing and let me distinguish a bit of terminology in between what we call matching and merging. So if I think of them in sort of combining 0, 1, and 2-jet topologies with a parton shower in one inclusive sample without double counting, then I can think about that I would have all of these topologies available at leading order, and I will get a double counting with the parton shower, because surely this additional jet can enter a region where I would also have generated that by a parton shower engine. And the process of using these at leading order and combining them into one sample, that is what we call leading order merging in this case. Whereas matching truly is about having this topology available at next to leading order. So we have virtual corrections, unresolved real corrections to this, and we have real emission, leading order production of that additional jet. So the next to leading order matching would take into account these two contributions here and would then combine them with a parton shower. In the same way, it would need to deal with the fact that we could have produced that jet by the parton shower or by the fixed order next to leading order, and we'll also see that there's an overlap in terms of virtual corrections. Now, if I can also get my hands on next to leading order corrections to that first jet bin, then I can think about combining all three of them at next to leading order for the first and for the 0th and first jet, and then I have leading order for the second jet, and this is what we refer to as next to leading order merging. This will be the topic of tomorrow's lecture, and then we can actually use the unitarity properties if we don't have a good enough parton shower at hand, and combine this with next to leading order correction for this lowest jet multiplicity. And here you can already see that I've been talking about the abilities and the accuracy of the parton shower, and this will be crucial since we sort of employ the availability of additional jet multiplicities at higher orders, together with the fact that we know that these logarithms must cancel to combine with next to leading order, but we can't perform that matching. Well, there's some recent attempts to do that, but until a few weeks ago, we couldn't really do that in a way that we could do this point by point, which is the procedure I will now outline for next to leading order matching. As a warm-up, let's consider what we call matrix element corrections. So matrix element corrections are sort of a bit looking at the parton shower and trying to fix it up where we possibly can with better knowledge. So assume that we look at parton shower emissions from just the leading order process, possibly the first jet order. And this is something which we can easily calculate by available automated amplitude libraries. And then we could say, okay, why do we actually need to resort to the parton shower approximation where we factor things from an n+1 parton cross-section? So in this case, I've been very explicit, because this will be some of the gory details we need to watch out for, is that, of course, if I'm expressing the n+1 parton phase space in the parton shower variables and the n parton phase space, I will get some Jacobian factor here, depending on that mapping, and this I need to take care of. But this is something which can be included, and with the motivation about matrix element corrections is essentially to undo that step as often as we can. Typically, and also widely available for the first emission, and that's something which has been pioneered by Torbjörn and Mike several years ago. Tens of years ago. And in that plane I advocated earlier, what will happen is that we start to fill in the first jet leading order matrix element, and then we can start the parton shower of this. Now you can see that explicitly the contributions which we double count in between these two jet bins, as we might change the boundary where we distinguish 0 from 1 jet. So this is something which we need to fix up. In the case of matrix element corrections, it's typically done by either improving the entire parton shower or choosing different phase space regions where we use the parton shower as opposed to the full matrix element. And this is more something like a merging approach then. I'm just bringing up this slide here to tell you that one thing we lack is of course virtual corrections, which would give us access to that correction over here. If we had the best possible parton shower, which would be able to reproduce everything else, which it will not be, and we'll see this, but to a good approximation, it will be doing this. But still, the thing we gain is that we will still inclusively only get the leading order cross-section back, because also if we expand the parton shower to the first order in alpha S, which is a very important concept which we'll be looking at now, we will still observe parton shower unitarity, because the Jacobian here is object here, is this Jn here. I have the same kernel in my virtual corrections, and I have the same kernel in my real corrections. In here, I've chosen to rewrite everything in terms of the real emission phase space. So also the parton shower evolution variable becomes a function of the real emission phase space. And we have limited the parton shower in between some hard scale capital Q and some small scale infrared cutoff scale mu. Still, this will deliver us for the first jet. If we ask for a first jet by this U of phi n+1, we will get the accuracy from the full matrix element if we replace this object here by inverting our approximation. But still, if we integrate over everything, we'll only get the leading order cross-section back. So shapes are okay, but the normalization is not yet NLO, and this is what we're going to fix up in the next thing. So one advantage we have is that we can use concepts like matrix element corrections to restore some of these color and spin correlations, and they will remove one problem in the matching I'll point you to in a minute. So let me not discuss this in detail, but we can employ that concept even in the case where we don't calculate the full real emission matrix element, but only certain properties of it which we wouldn't have otherwise. So let's start from expanding out the parton shower. So what I've written down here is the end parton cross-section. I'm tracing this up with parton shower emission starting from a hard scale Q down to an infrared cutoff. And then in expanding out the Sudakoff form factor, the first time I get 1, so I get back my leading order cross-section, nothing happened. And then I get a contribution which looks like a virtual correction, which is simply minus the integral over the splitting kernel. And then I get a real contribution. As I said, again, I have deliberately chosen to invert the phase-space factorization. So I have expressed my splitting kernel as a function of n+1 parton phase space. And I have an underlying Born matrix element squared at some kind of projected Born phase space point, but I still retain the parton shower phase space, so it won't be able to generate arbitrarily large PTs. And it is, of course, by itself finite in the sense that we have imposed an infrared cutoff where we would need to hand over to hadronization. But what this object here gives us is the necessary level of control that we can remove double counting, not only in between the parton shower and the fixed order generated jets over here, but we can also remove the double counting in the finite contributions, and we can impose a constraint on our matched cross-section or our matching subtracted cross-section that we really reproduce the exact next to leading order cross-section plus higher orders in alpha S as we act the parton shower on this. And that we still try and maintain unitarity in the sense that if we integrate over the parton shower, acting on a matched next to leading order cross-section, that we get back the full next to leading order cross-section. And this is the condition which is solved by next to leading order matching, and I'm going to discuss how this works now. But let me start with illustrating this rather in a simple way, in just kind of, again, a simple PT spectrum that could represent any infrared sensitive observable we're looking at. It's always the same feature we're looking at. So in this case, it's the PT of the Z boson, to be definite. And if we look at what just the leading order plus parton shower would give us, we have the following. Leading order cross-section, remind yourself, the leading order cross-section for producing the lepton pair might have some boost, but at leading order, it will balance in PT. So the PT of the Z boson will always be 0 in this case. And so we will get one entry, which is just the leading order cross-section times the probability to not emit down to the infrared cutoff. That will sit in that 0 PT bin. And then the shower will generate the physical peak in the PT spectrum at low speeds. And it will, I'm sorry for the noise, I don't know what that is. And it will stop at the infrared cutoff if we had cutoff parton shower radiation exactly in PT proportional to the transverse beams. And then it will also stop at a scale where we need to impose a cut on the hardness of the emission of the parton shower because it is simply not any more reliable and our approximations break down. And equivalently, having said that, we will here enter a region where we just assume that these particular logarithms are not large anymore. So this is why we typically stop the parton shower at this scale. And the area under this curve here is just 1 minus the no emission probability times the leading order cross-section. So this is parton shower unitarity at work. We just get back the leading order cross-section as we integrate over everything. Now, if we were to calculate next to leading order corrections, we get that weird spectrum. So this is obviously not a physical spectrum because we have this gap here, we have this delta function here, we miss entries in the tail. The next leading order, on the other hand, is giving us the tail from the real emission. And it's giving us the proper normalization, but again, the normalization is sitting in the divergent contribution here. And what we want to do is to combine that to really get the best of these and combine them into something where the shower gives us the physical behavior in the peak and the right answer in the tail for the real emission, and then a no emission contribution, which is fixed, that we reproduce the next to leading order cross-section. That's still a non-physical spectrum, but the gap we observe here is then later on being taken care of by either intrinsic transverse momentum or hadronization, which I'm sure you'll be hearing about in the lectures or have already heard so in the general Monte Carlo. So this is pictorially what we solve in terms of formulae. We really start from from what we obtained, the expansion of the parton shower to the first order in alpha S, which I've written down here. And if you look at this and compare it with the next to leading order correction, we have had the virtual plus the integrated subtraction term. Now, this is not very thrilling. This will just give some finite number. But the interesting part is in here where we have real emission for phi n plus 1, subtraction term for phi n. And this looks quite similar. We've got a phi n over here. We've got a phi n plus 1 over here. And so the question is, how can we combine them into each other so we satisfy this correction? And that combination is then pretty obvious, because if we have this is order alpha S. Now this will be order alpha S. And if we subtract this from this and act the parton shower again on it and expand to order alpha S, then we will be getting back exactly the next to leading order cross section. So let me make this explicit. So if I act on what I call my matching subtracted cross section, this has a part which is the leading order, and then we have an order alpha S correction, which is having the NLO correction in it, and then we have a matching subtraction. Let me move it, got a bit too little space. So we do have the matching subtraction. So this is not the subtraction, but the matching subtraction. And now if we simply expand this out to first order in alpha S, then we see that we can adjust this to be just minus the parton shower contributions at order alpha S, and we will get back what we demanded, namely the next to leading order cross section for plus higher orders in alpha S. So we have the real emission, we have the subtracted real emission over here. So I wanted to use the pointer here. We have the parton shower contribution at order alpha S, and at this point I have chosen to write everything in terms of the real emission phase space, which I can, which is something very important about parton showers as well, that we're able to directly cast the virtual contributions into an integral over the real emission phase space. So here I've just used the phase space factorization for this integral over the splitting kernel, which was sitting in the Sudekov form factor, and I've recast it into a real emission. But now I observe that again I have an emission contribution with no emission contribution, and they again appear in that very peculiar combination, which looks like a plus distribution. But now we have that sitting in terms of a real phase space. And fulfilling the NLO matching condition, then, as I said, is that we take the subtracted real emission and the other parts of the next to leading order correction. We subtract what we double count by the parton shower in order alpha S. That is the matching subtracted fixed order cross section. And if we act the parton shower on this calculation, then we will be reproducing the next to leading order plus higher orders in alpha S. So what I'm looking at here is exactly, this is a more precise picture of what I've shown before. So here we see the leading order plus parton shower, which will die out at a certain scale. And then we have the next to leading order in green, which will here go onto the red curve, which is the next to leading order fixed order. And from this, which is this object here, so this is the green curve in my picture here. From this, I will actually subtract the other contribution, that black dashed curve, and the black dashed curve, the real emission part of it is precisely this contribution over here, and I'm subtracting this from the real emission cross section, and I will then obtain two contributions. And the important point about these two contributions is that I will have one which is sitting in the n+1 parton phase space. So let me be explicit. So one of them is integral of the real emission matrix element I'm skipping the subscript, let's just encode this by the color. And then we have the shower approximation to it. So this is a leading order square at a mapped phase space point, which is capital phi. And then we have the parton shower kernel being function of the n+1 parton phase space. And we still have the infrared cutoff. And then we integrate over real emission phase space. But notably now we have the same observable sitting here, and a similar thing is going on for the subtraction term and the virtual shower contribution. Now the point is that we have two mappings in here. The shower might actually have a different mapping than the subtraction term. And one lesson we have learned in designing parton showers in the last 2 years or so is that using a subtraction mapping might by far not be the best idea for constructing a parton shower. And so this will complicate this picture a bit, but it's a solvable problem. We would need to calculate one Jacobian with respect to this one mapping and translate it to the other mapping. So this is a technical issue. The more severe issue we have in here is that we would still not be able to build an event generator out of this. And this is for the sake that even if our parton shower was constructed that it would have the same singular behavior as the real emission matrix element, possibly including all of the color and spin correlations, which we would be able to stick in using matrix element corrections or color matrix element correction, it's still got the parton shower cutoff here. So this would not allow us to generate a finite event, because as we go singular, this contribution would all of a sudden be switched off, and the real emission matrix element would diverge without anything being there to cancel it for this n+1 parton multiplicity. And we work back to the problem we had with the fixed order next to leading order calculation. But if you think about it, if U is an infrared safe observable, I can actually have a go and add another contribution here, which is of, again, this type, leading order times splitting kernel times U of phi n plus 1 minus U of phi n, some mapping here. And then I wouldn't want to constrain this to live below the infrared cutoff mu minus Q of phi n. Plus 1. Now, if U is an infrared safe observable and we properly partition V into different collinear sectors, then we can actually observe that this is a power correction in the infrared cutoff. So our matching condition will still be exact in terms of orders of alpha S, but it might be spoiled by corrections, by power corrections in the parton shower cutoff, but this is a thing we can live with. Patronization is a similar issue. And then it's about sort of having done that, different next to leading order matchings only differ by different choices of what the parton shower is. That one we obviously need to fix, of what this retwiddle is and what in the end subtraction terms are to be used. But their dependence does not impact the next to leading order matching. So there's a bunch of ambiguities in this. One of the ambiguities is retwiddle, but I'm not worrying about this one. The much more significant ambiguity is in the limitation of the parton shower towards the hard scale, and that we'll discuss in the last couple of slides. But before doing so, let me just sketch what will happen if we chose a parton shower with a matrix element corrections to be matched to. So we start from our matching formula, we subtract the shower approximation. Now, what would happen if we would improve that parton shower by a matrix element correction? We would replace this by the real emission matrix element. And if you do this, then we end up with this contribution here. And this is quite an interesting thing. So I've been skipping the parton shower infrared cutoff again. But this, if you work it out, what we see here is that we have phi n plus 1, which has a weight times real emission matrix element times the complement of the parton shower phase space. So if I think about this, let's say this is the complement of the parton shower phase space. In this case, this would only be populated by the real emission matrix element squared. And then I would have some parton shower domain below here. And in particular, this match calculation would be extremely simple because I could choose, say, I could build a parton shower which would be able to populate the entire phase space for one emission. And then this contribution with n+1 partons would just go away, and we would be left with a local K factor, just the inclusive next to leading order correction to start our parton showering with the matrix element from. And this is essentially the Pauhek method in its simplest form. And it's becoming more complicated if we shuffle things between the real emission region and the parton shower region. And this is also a problem which we always hit if we would not do Pauhek, also if we would just do a simple next to leading order matching as I've sketched it before, in that we will need to cut off the shower somewhere. Now, if we do that by a hard cut, then we'll observe that there will be a step, and you can convince yourself that that step is of next to leading order size, so there's no chance for us to get that under control. So what we do is that we instead take some smearing of the shower cutoff, and this is happening in all event generators as far as I'm aware. And notably in Pauhek has chosen a very broad smearing. Also something similar is happening in AMC at NLO, if I'm not mistaken. In Herbig, we have a narrow smeared approximation, and then there's a whole of discussion we can have about how this impacts the properties of the shower. Another thing which I wanted to mention here is that very often this hard scale at which we make the transition in between parton shower and matrix element is referred to as a parton shower starting scale. Now that's not quite true, and it's especially not true for an angular ordered shower. So it would be true if we would look at a PT ordered shower, which I've just sketched here. So we start with hard large angle, another hard large angle, and then we go on to smaller and smaller PTs. Could be a large angle soft emission, which has an angle much larger than this. So we can use these parton showers, we can correct for the issues which Stefan has been showing you in the previous slides for all of these color factor things and so on. But still the issue remains here. We have a starting scale which we can limit emissions on PT, but if we use an angular ordered shower, that won't work, and we can have the hardest emission somewhere in between, and that necessitates the use of truncated showers, which we'll be discussing in the context of merging in quite some detail. So this limit is not the hardest scale, but not the shower starting scale, but just some hard scale. So I've been told I should stay strictly in time. Let me just flash the last two slides. One of the things in our multi-purpose event generators which really made us able to use next to leading order matching off the shelf is really the way that we could be automating this, and automating this not only for the amplitudes we need for the loop integrals for the real emission, but also automating this in terms of the subtraction terms and the next to leading order matched subtracted, and then some kind of merging machinery downstream. And this is, I think, an extremely nice example of different components working together. Each of the colors, by the way, here is showing you a workflow for one of the multi-purpose event generators. We can discuss that later. As an upshot, here's a table of what the current status is. Mainly not talking about next to leading order capabilities, but just next to leading order. That's a comparison between Herbig, Pythia, and Sherpa and different capabilities. And I wanted to focus your attention on what I've just been talking about and will be talking about tomorrow. That is the capabilities of calculating hard matrix elements, either by internal libraries or event files or external libraries. And notably, matching and merging functionality for Herbig 7 and Sherpa, which has everything automated internally, and then Pythia has automated merging internally, but needs to use external tools for matching. And I think with this one, I wanted to finish for today. I'll leave you with a few example plots, some historic ones, and some recent ones. And just wanted to say that we really have now very powerful tools which we can combine with shower and matching variations and variations of the hard process to assess the accuracy of the next to leading order perturbative predictions in event generators. Thanks.
Great, thank you, Simon. And again, we'll have time for Q&A during the recitation this evening, again at 2000 European time. So what we will do now is we will go to the tutorials, and that is in a different Zoom room. So if you go to the main timetable, you can select your tutorial, and then you'll have to go to that individual Zoom room. So we'll sign off now, and thanks, Simon, again, and we'll catch up with you later. So thank you, Simon.
Thanks a lot. Talk to you later.
Okay, bye.
Bye.